Okay, everyone, welcome back. Now let's look at this same idea, but we're going to do this idea now using Gaussian elimination. Now, to do this, I said we want to build a coefficient matrix. There's actually a special word for this type of matrix that we're going to build. So first, we'll do the coefficient part of this matrix. So my coefficients are, for the first line is 2, 1, 1. So it's going to be 2, 1, 1, 0, 3, 4, and 6, 0, 1. Okay, so that's it for the coefficient part. And normally when we build our coefficient matrix, we normally just close the bracket in and then we would write x, y, z like this over here. And then we'd have our solution over on this side, which in this case would be -1, -7, and 8. So our solution would be -1, -7, and 8. That is normally how we would develop this matrix when we're solving via simultaneous equations. Now, because this is kind of the case with so many of these, we actually create what we consider an augmented matrix. There's a couple of really good reasons why we want to do an augmented matrix, but first let's just start by what that actually means. An augmented matrix means I essentially, because I know I have 3 variables, x, y, z, I don't actually mind what my variables are called. So it could be x, y, z, it could be a, b, c. I don't really mind. These are going to be my algebraic letters or my solutions. So I don't really need to put in my x, y, z part. Or when we consider this idea of how we can write this more easily, we don't really need my XYZ part. I just know my 3 solutions at the end are going to be whatever my 3 variables are in my question. And I should also note that my columns will still be variables X, variables Y, variables Z. You can see if I look at this whole column, these are all my X coefficients, all my Y coefficients, all my Z coefficients. So I still know I'm going to get my 3 answers in terms of those 3 variables. So I don't really need to put the XYZ part here. I also have it equal to this answer, but I'm not actually trying to figure out what my answer is. I'm trying to figure out what my value of X, Y, and Z are. So instead of writing it equal to those variables, I'm going to get rid of my equal sign. I'm going to get rid of these 2 brackets here. I'm going to drag this part all the way across and create one big matrix. So I've augmented my solution matrix to my normal matrix. Now, just to distinguish that this is an augmented matrix, we normally also will put a line in here as well. So it's going to be my coefficient matrix on the left-hand side of that line and my solutions on the right-hand side. And what I've created now is a big matrix. It's no longer a square matrix. Create a big matrix with a series of numbers where on the right-hand side I have the solution, on the left-hand side I have my coefficients. Now, if I make this look slightly neater, I'm just going to draw in my line here like so. Okay, so this is my augmented matrix, my coefficients on the left-hand side of my line, my solutions on the right-hand side of my line. Now, what we know when we're doing elimination method, essentially what we're trying to do here is we are trying to eliminate one of my variables. You can see if I look at this example here, one of the ways to think of this operation of 3 minus 1 is I'm making the coefficient of z 0. 1 minus 1 gives 0. My coefficient of z is 0. So really when I'm doing elimination method, all I'm really trying to do is make my coefficients equal 0. You can see here my coefficient equals 0 again. Even when I do my final part of my elimination method, I'm still trying to make my coefficient, in this case, of my y's equal 0. So I'm left with just an x. Now, if we come back to my coefficient matrix, what that means is I want to eliminate, using my Gaussian elimination method, I want to eliminate like this number 6, for example. So I'm left with is a little pocket where I just have zeros in this bottom corner. Because if you think of it, if I just have zeros here, if I have 0, 0, 1, and then some number, let's say this is 4, for example, then that means that I have 0 lots of x, 0 lots of y, which means I have z is equal to 4. So that then I can solve for one of my variables. Once I solve for one of my variables, I can start substituting in. So sometimes the way you're going to see this is with a matrix that looks like 1, 1, 1 on the leading diagonals, zeros everywhere else. Here's my augmented part, and I have x, y, z. If we get this situation, my bottom row here is going to be equal to z. And if I put zeros here, then my top row is going to equal x. My middle row is going to equal y. So this has a few different names. Sometimes this is called an upper and lower triangular matrix, or sometimes this is called row reduced echelon form. Just note, we don't always need to have zeros above these ones. For example, I could just have, let's just say I have A, B, C. If I have some numbers above them, that's fine as well. As long as we get zeros in this lower triangle here of our matrix. As long as I get my zeros here, then I can find Z. Once I find Z, I can sub in to solve for Y. I can sub in to solve for X. So I want to use what we call row operations to essentially use my current 3 equations here, add, subtract, multiply, divide them together to create a pocket of zeros in my lower 3 elements, or my lower 3 entries. For those of us that might be a little bit unsure as to kind of how we do that or what this all looks like, or just want to see an example, just try to bear with me. Let me go through the whole process and then we'll see if it makes a bit more sense after we've looked at it. Really, all of chapter 6 is just kind of building towards this idea. So really 6b, 6c, this is as hard as it's going to get. So it's kind of the same idea in both of these chapters. So I've got my augmented matrix here. And now I want to start doing row reductions to get this number here in place to be a 0. So I get this number here to be a 0. So my bottom line just equals Z. And I can use that to substitute it. If I call this row 1, row 2, and row 3, I want to perform row reductions. So I want to use my current rows. I want to scale them, either multiply them or divide them by different numbers to create a situation where I can eliminate my coefficient. So if I look at my matrix, there's only one option I really have because in row 2, I have a 0 for my x's. And again, I want to make my 6 equals 0. So I have to use row 1. And some of you might be able to see, okay, well, if I take row 3 and I subtract that by 3 multiplied by row 1, if I times everything here by 3, 3 times 2 is going to give 6. I can then eliminate my 6's. So let's do that process here. The way we write this out is because I'm just performing this operation to row 3. Everything else is going to stay exactly the same. Just now for this row, it's going to be my new row 3, which we call R3 with a little dash, is going to be equal to the original row 3 minus 3 times row 1. If I do that, well, that's going to be 6 minus 6. So I will get my 0. 3 times 1 is 3. So 0 minus 3 is going to become minus 3. This is going to become minus 2. And I'm going to have 8 minus 3. That's going to become 11. So this is my new row 3 here. Let's actually change the color. Let's make this in green. So let's put that in green. That's my new row 3 that I have here, where again, I'm trying to essentially create some eliminations to get some zeros. So now that I've got that, you can see I've got a pair of zeros here, which really makes life easy because now I can add or subtract by any scale factor. If I do that, I'm still going to wind up with 0. So I times row 2 now by 3, I still have 0 on my outside term. So when I have the 0 pair, that really makes my elimination process a lot more straightforward. So let's do the same thing again now. Let's just do new row 3 and we'll add that to row 2. Okay, so my new row 3 is going to be equal to row 3 plus row 2. Now, just note my row 3 is referring to the row 3 I found up here. So if I go ahead and do that, that's going to be 0 plus 0, which is, let's do green again, is 0. 3 or minus 3 plus 3 is also going to give 0. Minus 2 plus 4 is going to give 2. And 11 minus 7 is going to give 4. So I actually have a few options now. If I really want to make this 1, you can see now I can just divide row 3 by 2. I'm happy to do that, or I could separate this and say, well, that's 2 lots of Z is equal to 4. I could find Z that way. Just bear in mind, these numbers here represent coefficients of my letters. Just for the sake of making it with 1s, let's just go ahead and divide everything by 2, because I just like looking at it in that way. Okay, so if I halve row 3, I get this line here. Okay, so now that I've got my little triangle of zeros in this bottom corner, and I had the same triangle up here as well, I can now just say, okay, well, Z's going to equal 2, Z's going to equal 2, and I can use that Z equals 2 to substitute into row 2, and substitute that into row 1. So I do that, that's going to become 3y plus 4z equals minus 7, becomes 3y plus 4 times 2 equals minus 7. So that means 3y is going to equal minus 15. So y is going to equal negative 5. I now know z, I know y. I can substitute that into my top row, which is going to be 2 lots of x minus 5 plus 2 is equal to minus 1. Subtract 2 off each side, add 5 to both sides. I get 2x. I guess I could actually just add 3, right? 2x is equal to 2, so x is going to equal 1. Therefore, x equals 1, y equals minus 5, and z is equal to 2. So whilst it feels like we're doing a lot harder work here to figure out my solution originally, it really is just because we're so much more familiar with elimination method. Really understanding this process here, it can get quite quick. You can also do multiple row operations at the same time as well. I would recommend do 2 row operations max. So for example, I could do, if I want to eliminate both row 3 and row 2, I could also be doing, new row 2 operations at the same time and kind of save a bit of time that way. It just depends, as long as it makes sense in your mind, and you're not making mistakes, it's fine. So that's an example of how to do it with these numbers specifically. Feel free to have a go using that method, to have a go at 2, 1a. Actually, we'll do all of question 1 using that method.